to this. Welcome to the Explainer. Today we're taking our very first steps into actual real-world machine learning. You know, if you've ever wondered how AI predicts things, like say, what your future salary might be based on your years of experience, well, you're exactly in the right place. Today we're looking at a concept called linear regression. Now seriously, do not let the name intimidate you. This is literally the absolute foundation of machine learning. Pretty much every data scientist, every AI engineer, every machine learning expert out there, they all started right here. We're going to build your understanding completely from zero, step by step. By the end of this explainer, you're going to know exactly how it works.
So here's our roadmap for conquering this together. 1. We'll meet linear regression. 2. We'll make the math super simple. 3. We'll see exactly how the algorithm learns. And 4. We'll look at the real world and the code. Let's get to it.
All right, Section 1. Meet linear regression, finding the best straight line.
So what is it? Basically, linear regression is a supervised machine learning algorithm that models the relationship between variables using a straight line to make predictions. Okay, let's break that formal definition down into plain English. Supervised just means we're feeding it data that already has the answer so it can actually learn by example. Its entire job is to figure out the relationship between a dependent variable, that's the thing you want to predict, and one or more independent variables, which is the information you already have. And it does all of this just by drawing a straight line. It's kind of like a giant puzzle, and it finds the absolute best straight line that fits your data and uses that line to make future predictions. Imagine you want to predict a person's salary, right? You have data on their years of experience. Linear regression looks at all that past data, draws a line right through the middle of those data points, and suddenly you can pick any number of years of experience, follow that line, and predict the exact salary. It's really that direct, and honestly, that powerful.
Moving right along to Section 2. The math made simple, from geometry to algebra.
Now, if the word math makes you a little nervous, just take a deep breath. It all boils down to y equals mx plus b. You probably remember this from middle school geometry, right? This is for simple linear regression with just one variable. So y is our predicted output, like that salary we want to guess. X is our input feature, the years of experience. But here's where we translate middle school math into machine learning. That m, which you might know as the slope of the line, we call that the weight in machine learning. And b, the intercept, that's what we call the bias. This is absolutely crucial. This simple equation, balancing weights and biases, doesn't just stop here. If you add more variables, like maybe factoring in education level or location, the equation just gets a bit longer. But fundamentally, this exact equation is the backbone of advanced neural networks. You're literally looking at the DNA of artificial intelligence here.
Now, to put that into perspective, if we only have two variables, like experience and salary, we're operating in 2D space. The algorithm draws a best fit straight line on a flat graph. Pretty simple. But what if we have three variables? Well, we enter 3D space, and that straight line actually expands into a flat sheet or a plane, slicing through a 3D cloud of data. And what if we have dozens or even hundreds of variables? Human brains definitely can't picture that, but the math handles it beautifully by creating what's called a hyperplane in higher dimensions. But listen, no matter how complex the data gets, the core mission is always the exact same: fit a flat surface through the data to make predictions.
Which brings us to Section 3, how the algorithm learns, minimizing the error.
We know what it's trying to do, but let's open the hood and look at the engine. How does the machine actually learn?
It's a great question, isn't it? Machine learning can sometimes sound a bit like magic, but there's no magic here. Just a really clever, repeatable loop of trial and error. Let's completely banish any intimidation here. Here's the learning loop demystified in 3 easy steps. Step 1. The algorithm starts out clueless, so it just draws a completely random line through the data. Honestly, it's a terrible guess. Step 2. It measures exactly how terrible that guess is. It measures the vertical distance between all your actual data points and that random line it just drew. That distance is called the error, or the residual. It squares those errors to make sure negative and positive distances don't just cancel each other out, and then it finds the average. We call this the mean squared error, or MSE. Then step 3. This is where the real learning happens. It uses a process called gradient descent. Think of it kind of like a hiker taking small steps down a hill in the dark to find the lowest valley. The algorithm tweaks the line, adjusting the weight and bias to step down that error curve and make the mistakes smaller. And then, it just repeats this process thousands of times. Guess, measure the error, tweak the line. Guess, measure, tweak. It loops until the error is minimized as much as absolutely possible. When it finally stops, that final line is your fully trained machine learning model. How cool is that?
All right, let's wrap this up with Section 4, real world and code. applying linear regression.
Now, for the algorithm to perform at its absolutely best, statisticians rely on a few underlying assumptions. Don't let words like homoscedasticity scare you off. We're going to keep this super practical. First, it assumes there actually is a linear relationship between your inputs and outputs. I mean, you can't really fit a straight line to data that naturally moves in a wild squiggle, right? Second, no multicollinearity. That just means your input features shouldn't be too deeply correlated with each other. Third, homoscedasticity. This just means the errors, those distances from the line we talked about, should be relatively consistent across the whole graph, not just fanning out wildly at one end. Fourth, the observations should be independent of each other. And fifth, the residuals, or errors, should ideally be normally distributed, sort of like a bell curve. When your data meets these conditions, linear regression is an absolute powerhouse.
But, like any tool, it has its pros and cons. Looking at the advantages, it's incredibly simple to understand. It's extremely fast to train even on massive datasets. And it's highly interpretable. You can look at the weights and see exactly how much 1 year of experience adds to the final salary prediction. There's no mysterious black box here. But on the flip side, the disadvantages. If your data is highly complex or nonlinear, this algorithm is going to underfit the data, meaning a straight line is just way too simple to capture what's really going on. And here's a huge caveat. It is extremely sensitive to outliers. Because it's trying to minimize the squared error, one single crazy data point, like say a billionaire hiding in your salary dataset, can literally pull and tilt the entire line way off course. So, with all that said, how hard is it to actually build this? 7. It takes just 7 core lines of Python code using a super popular library called scikit-learn. No way, right? 7 lines. You split your data, call the linear regression model, hit fit to train it, and hit predict to use it. That's the whole shebang. All that math, the mean squared error, the gradient descent looping thousands and thousands of times, it's all handled under the hood in a fraction of a second with just 7 lines of code.
And because it's so fast and easy to implement, it's driving massive decisions across industries right now. Real estate platforms use it to estimate the price of a house based on square footage. Businesses use it for demand forecasting to predict next month's sales. It's used in agriculture to predict crop yields based on rainfall, and in engineering to estimate fuel consumption. It is literally everywhere you look for continuous numeric forecasting.
So, what does this all mean? The crucial takeaway here is that linear regression is simple, yes, but it is the bedrock of everything in machine learning. The concepts of weights, biases, errors, and gradient descent that you've just mastered today, they are exactly what power advanced deep learning. Which leaves us with a really fascinating question. If this simple straight line is the foundation of all neural networks, what incredible predictions will you build with it next? You've got the foundational knowledge now. In our next explainer, we're going to take these exact same concepts and bend that straight line to solve classification problems using logistic regression. You definitely won't want to miss it. Keep learning, keep questioning, and I'll see you in the next explainer.